We're considering a $25,000 loan to be paid in equal installments at the end of each year of the next 5 years. So first thing is we need to identify our cash flow that we're working with. There's a lump sum today that's going to be repaid in a series of 5 cash flows that are equivalent over the next 5 years. So it's a cash flow that begins and ends. So we're obviously working with an annuity. Hence we have the annuity formula already presented. So we need to set up an amortization schedule for a loan. And then we were going to see how large must each annual payment be if the loan then is in $50,000. So we can set this up in Excel starting at 25, and we'll just change it to 50, which is kind of nice if we do in Excel. Assume that the interest rate remains at 10%. So if we keep these key inputs, it'll be pretty easy going forward. And it's paid in 5 years. So it's like our first one, except we're going from 25,000 to 50,000. So not much of a difference. How large must each annual payment be if the loan is for 50,000 and the interest remains the same at 10%, but it's paid over 10 years? That is, the rate then remains the same, but the time period doubles. So this is kind of like if you're going from a 15-year loan to a 30-year loan and for a mortgage. So for those of you who don't have a mortgage, but at some point you will, this is where this becomes relevant. So if you go from a 15-year mortgage to a 30-year, in this example, we're just going from a 5-year to a 10-year. Then part 2, note that the loan in part C is the amount is a B, but we need to identify why the payments are spread over twice as many periods, but why the payment in C is not half a B. So we'll talk about that. All right, let's get down to it. So what does our cash flow look like? Well, we have at time 0, there's a loan of 25,000, and then we're going to have an outflow of 5 payments, one each year, that pay back this amount of 25,000. So the direct way to get to this is use the payment function in Excel, as you've learned in earlier solutions. To set this up as the annuity, we have 25,000 is equal to CP, and then the rest of our inputs are known. We know that the rate is 10, the time is 5. We solve for this to isolate for CP. So all we essentially do is leave CP on the right-hand side of the equation and move this term, the annuity factor, to the left-hand side. So since we're multiplying here, we divide both sides by this term, and we find that we have CP is equal to 25,000 divided by 1 minus 1 divided by 1.1 to the power 5, and that's all, of course, then divided by 0.1. So we see that the payment each year is going to be $6,594.94. You can also double check this just using the payment function. So equal sign PMT. Our rate is 10%. We know the number of periods is 5. The present value is 25,000. So at time 0, it's cash inflow. So we expect outflows at years 1 through 5. There's no future value, and we know it's at the end of the year, so it's by default an ordinary annuity. If you want to force it, we'd type in a 0, but by default, that's what it is. So we're done entering the arguments into this function. Okay, equal sign, and there we go, perfect. It adds up just the same. In part B, the only difference here is now we have 50,000, right, instead of 25,000. We work through everything and we find, 13,089.87, so it's literally double. So as the loan doubles, the payment doubles. We can then copy our formula, carry it over, and to double check, and we see that our solution doing it the long way is correct. In part C, now the time period is doubled. So it's the same as B, but now T, that was equal to 5, is now equal to 10. And this carries into the second part of C. So we solve for this, and we find that the cash payment is $8,137.27. If we compare that proportionally, we'll make some interesting, or we'll find out that it's not half of what's in B. So we'll again paste our formula over, and we see that, yep, the function, using the function confirms that our long way, or a long solution was correct. And now what we'll say is, well, here's our original amount, and we'll divide it by the amount that when the time is doubled. And so normally if B were twice as much as C, we'd expect this value to be 2, but it's only 1.62. So going back to C part 2, why is it payments in C are not half of B? The other way we can test this is say equal to C divided by B. We can see that they're greater than half. And the reason being is, remember, the payment is doing two things. It's accounting for that interest component, or returning the rate of return of 10% plus the principal amount. And for that reason, it's not going to be half as much. Now, if R goes to 0, then it will be half. But as we start to impose a rate of return, we depart away from this 50%. So as we go back to 10%, we now see that even though the time period doubles, it's not half as much in terms of payment. And we can compare this to if we did a 15-year and a 30-year. Now look what happens. So we see with the 15-year, we only need to pay a little bit more, proportionally, 25% more, to cut off 15 years. So we'll talk about the mortgage application down the road and as time changes. But I wanted you guys to see this, and this will help you, of course, in answering 420, but having a little bit more insight in terms of how term influences